Infrared radiation is part of the electromagnetic spectrum. It was discovered by William Herschel, who found that when he separated light from the sun into its different colours, beyond the red colour, invisible to the eye, there was some other radiation that caused the temperature to rise. Infrared radiation can cause bonds of molecules to vibrate by stretching and bending them. The frequency of the infrared radiation which causes the bond to vibrate can be characteristic of the bond. For example, consider the carbonyl group C double bond O. When infrared radiation in the range 1640 to 1750 cm to the -1 is directed towards a molecule containing C double bond O, this radiation is absorbed by the bond, causing it to stretch. How the instrument works. A thin layer of sample is placed between two sodium chloride discs. Sodium chloride is transparent to infrared radiation. A scan is made by running different frequencies between 450 to 4000 cm to the -1. The different types of bond within a chemical absorb infrared radiation at different frequencies, since bond strengths vary for the different types of bond. When molecules absorb infrared radiation, not as much radiation passes through the sample, and so the response from the detector is low. In regions where the molecule does not absorb strongly, the response from the detector is high, as the radiation passes through the sample largely unaffected. A spectrum is then produced, where the wave number in centimetres to the -1 is plotted along the x-axis, and the detector response, or percentage transmittance, is plotted along the y-axis. The peaks in the spectrum show where bonds within the molecule have absorbed infrared radiation. In AS chemistry, you only need to be able to recognise a few key peaks. The CH bond causes a series of sharp peaks between 2850 and 3100 cm to the -1. Consequently, most organic molecules will show peaks in this region. A very important peak that you must learn to recognise is the carbonyl C double bond O peak, which gives a strong absorption of infrared radiation between 1640 and 1750 cm to the -1. You can think of this as a finger. Another important peak is one that results from the presence of OH in alcohols, which occurs as a broad peak between 3200 and 3550 cm to the -1. The OH peak in alcohols can be thought of as being like a thumb. The peak that results from OH groups in carboxylic acids is much broader than that in alcohols and is between 2500 and 3300 cm to the -1. You can think of this as a cucumber. Let's use our toolkit of the finger for the carbonyl, that's C double bond O group, that occur between 1640 and 1750, the thumb for the alcoholic OH, between 3200 and 3550, and the cucumber for OHs from carboxylic acids between 2500 and 3300, to distinguish between aldehydes, ketones, alcohols, and carboxylic acids. Let's try with this compound. Does it have the finger? Yes, it does. This means it has the carbonyl, that's the C double bond O group. Now let's check for the alcoholic OH with the thumb. No broad thumb-shaped peak present at between 3200 and 3550. Now let's try the carboxylic acid OH group. No very broad cucumber-shaped peak between 2500 and 3300. Our compound could therefore be either an aldehyde or a ketone, but with our present toolkit we cannot distinguish which one. Now let's try this compound. It does contain a finger, and so there is a C double bond O carbonyl group present. The peak over here is too broad for an alcoholic OH. The cucumber peak, corresponding to the OH of a carboxylic acid, fits, and so the compound is therefore a carboxylic acid. With this one, we can see it has a thumb peak in the correct position, confirming the presence of an alcohol OH group. There is no finger, and so no carbonyl group is present. Therefore, the compound is an alcohol.